let's do this. The previous time we stopped, I've covered most of this course already. It has 38 videos in it, and I've covered 32 of them, so I only have a handful to go. This one is in Ukrainian. I'll try to translate it. And the current topic that we are going to cover today is statistical hypothesis about variance in normally distributed data. So let's go.
Розглянемо статистичні критерії для перевірки гіпотез про невідому дисперсію.
I will try to translate the slides. I won't translate all his speech, but it's pretty similar to the slides. So
Нормально розподілених спостережень. Нормального розподілу.
So we got some data x1, xn from normal distribution with these parameters, and this chapter is about covers statistical hypothesis for distribution for variance in normal distributions. So our first example is when we have unknown mean in our normal distribution and unknown variance, and we would like to estimate it, right? So we create this null hypothesis. Null hypothesis in which we basically equal our unknown sigma squared to some known real number sigma 0 squared. So let's just write this down. So again, h0 is sigma squared equals sigma 0 squared.
З невідомим середнім м'я і невідомою дисперсією сигма квадрат. Найпростіша гіпотеза про дисперсію, яку ми можемо розглянути, це те, що дисперсія дорівнює фіксованому значенню сигма нульових квадратів. Ну і така гіпотеза також є, часто виникає в задачах контролю якості. Ми перевіряємо, що відхилення від еталонного значення нашої продукції не надто велике. Тому звичайною альтернативою такій гіпотезі про невідому дисперсію є те, що дисперсія велика. Те, що сигма квадрат більше оцього дозволеного значення сигма нульового квадрату. Це стандартна альтернатива для гіпотези про невідому дисперсію нормальних спостережень. Ну і знов таки, щоб побудувати критерії для перевірки такої гіпотези, нам треба стартувати з певної статистичної оцінки. В якості статистичної оцінки можна взяти вибіркову дисперсію.
So he's saying that we are going to take fucking shit. 1 second. We are going to take to calculate this statistic for this specific example. Statistic t can be formulated as n, which is size of our data set divided by sigma 0 squared. Sigma with hat, this is sigma squared with hat, that's an estimate of sigma, of original sigma, and this statistic, if h0 holds and it's true, this statistic has distribution of he squared with n minus 1 degrees of freedom. Very important. He squared n minus 1 if h null is true. So
Вибіркова дисперсія має розподіл Фактично пропорційний розподіл хі квадрат з n-1 ступенем свободи. Так ось ми для побудови критерію цю оцінку перетворюємо, а саме домножаємо на n, ділимо на гіпотетичне значення дисперсії, так, щоб в разі правильної основної гіпотези отримати фіксований розподіл хі квадрат з n-1 ступенем свободи.
So he's saying that the estimate of sigma squared, the one we had, is already has some chi squared distribution.
Знов таки, щоб побудувати критерій для перевірки такої гіпотези, нам треба стартувати з певної статистичної оцінки. Версія має розподіл, фактично пропорційний розподіл хі квадрат.
So he's saying that the sigma squared we had has distribution which is proportional to chi squared with n-1 degrees of freedom. So let me remind you that chi squared distribution is basically sum with n degrees of freedom is basically sum of n independent normally distributed variables, sum of these variables to power of 2, so squared independent normally distributed variables. In case of sigma squared, let's remind us that sigma squared has the estimate for sigma squared is 1 second. So it's basically here. So it's basically 1 over n. Yeah, so it's basically, I'll probably mention the photo here, but it's basically 1 over n times the sum of n parts, yes, sum that goes from 1 to n, and the sum of xi minus mean of x to the power of 2. So x minus mean of x is normal distributed data because our x's come from normally distributed data, and mean of x is just a number. So if you subtract normally distributed some number from normally distributed data, you still get normally distributed data to the power of 2. So that gives us independent variables, normally distributed independent variables squared, and their sum n times. So to make this, so the problem here is that our independent variables inside the sum, they come from normal distribution, but not from standard normal distribution. They come from some distribution with parameters mu and sigma squared. When we subtract mu from each point, we basically centered our distribution out, our data, so that makes the whole expression xi minus mu a variable that comes from normal distribution with mean 0. But still sigma squared is there. So to make this whole thing work, we basically multiply our initial, we do as he does. This thing has this distribution as we just described, right? If you multiply it by n divided by sigma squared, apparently what do you do? This. So I get the idea. He's just trying to remove that sigma squared from the distribution. I get the plain chi squared distribution. I get the idea. but I don't get it formula-wise. I don't understand how he got the formula. So let's try to derive it. So what do we do? Okay, we do what do? We say that sigma with the estimate of sigma squared is basically 1 over n sum from sum over I from 1 to n of xi minus mu to the power of 2. Now, if you go further, so we have so the standard normal distribution is just so he's basically multiplied this by sigma 0, right? Right. So let's try that. So if we multiply it by sigma 0, multiply and divide it, so we multiply just 1, but we multiply sigma 0 divided by sigma 0, we get xi minus mu divided by sigma 0 and everything to the power of 2. So in this case, xi minus mu divided by sigma should become standard normal distribution, right? This motherfucker should become standard normal distribution. Why? I guess this is called standardization. Let's double check. Math. Normalization, no, we need standardization. Standardization is another scalar method where the value is centered around mean with the unit standard deviation. This means if you will calculate mean standard deviation, it will be 0 and 1 respectively. So we transform, yeah, so this is what we do. We just basically transform our x minus mu divided by sigma, we transform it to standard normal distribution, and then we get he squared. Works. Why n minus 1? Because again, there is because of you. I believe because mu is dependent on the x's. So and the sum, yeah, well, they are dependent. X's are dependent on the mean of this sample, because sum of all of the subtractions xi minus mean, this sum always equals to 0. So that gives us n minus 1 degree of freedom, because we have I don't quite get it, but somehow we don't have one additional independent variable. Maybe that's true. So if you have n, if you sum over I from 1 to n of these xi minus x, the mean of x, then you will probably get one item which is dependent on others, because well, the way I try to study this is through understanding each detail. So I'm going and I'm gonna just Google it and have a look why is this the case. So let's try. He squared and variance. Let's try. Okay, I think I saw it. Okay, where's n minus 1? I think I saw it somewhere. Pearson's he squared. Here it is. Here is our formula. Okay, let's try to see it. Minutes. Still going.
I am answer your help.
Okay, so but set up blah 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 blah. This is for yes. Sample mean. Yes, this is the estimation for sigma squared. Then are independent. Yes. Okay, where do you get this from? Okay, yes, so this is
So you can look at the PDF. Math I've done, and then basically what it's saying is that if we take all of our observations and we subtract our sample mean, and then square that and divide by our population variance, that's equivalent to taking our sample variance, multiplying by n minus 1 and dividing by our population variance. And this proof is also quite simple. You just have to look at what the definition of s squared is. S squared is 1 over this thing over here, well, this sum over here. So if you multiply n minus 1, you're left with this particular sum, and then it's just, yeah, straightforward from there.
again, because there are two ways to calculate s squared. There's one way when you divide it by n, another way when you divide it by n minus 1. When you divide it by n minus 1, you get unbiased estimation, which is nice. Doesn't matter. In our case, we use n. In his case, he's using n minus 1. Whatever.
The second fact that we need is we need this fact over here, which is if you take the sample mean and you subtract the population mean, right? So you take the sample mean and you subtract the population mean for each of your random variables, and you square that, and you multiply it by n, and you divide that by sigma squared, then that random variable, or that little manipulation, that has a chi-square distribution of 1. And the basic idea behind this proof is if you take xn bar, remember xn bar is normally distributed, if you subtract the mean and you divide by the standard deviation, which is sigma over root n, you're going to get something that looks like xn bar minus mu multiplied by square root n over sigma, which is a standard normal because xn bar is normal. And then if you square a standard normal, you're going to be left with the square root of n squared is just n, the square root of xn bar minus mu is xn bar minus mu squared, and the square root of sigma is sigma squared. So that's all that's saying. So I basically walked through that proof verbally. And then the last point is this one over here, which is if you take your variance, but we don't now the proof.
Well. Again, he has n parts, but in the end he squared with n degrees of freedom. In our case, we got n minus 1 degrees of freedom. Why do we get n minus 1? Is there another explanation? Okay, no, there is.
Okay, now we can get to the proof. Now, the proof kind of is a bit weird because we don't really use MGFs. Well, we do use MGFs, but we don't do it in the same way. So basically, we can say that, well, it is MGF. So if we are proving that using our setup that we had before, that n minus 1 s squared over sigma squared is chi-squared with n minus 1 degrees of freedom by the method of moment generating functions, right? This is equivalent to saying that the MGF of this whole thing, so the MGF of n minus 1 s squared over sigma squared of t is equal to the moment generating function for v, where v is some chi-squared with n minus 1 degrees of freedom. So that two statements and that two proofs are equivalent. So where the bulk of this proof comes from is proving that this is, or this particular moment generating function is that moment generating function. And we start off in a weird place. Well, we start off with the right-hand side first, usually. So the right-hand side is just mv of t, which is 1 minus 2t. That should be a 2.
How would you like a free copy of...
I don't want any free copies, thank you.
So that is a 2. Okay, so that's just showing what the right-hand side is equal to. The left-hand side, that's going to take some work. So we're going to define this other random variable, which seems like it's coming out of nowhere, but we're going to define w to be the sum from I is equal to 1 to n of the following: xi minus mu squared over sigma squared. Okay, so this is basically just taking all of the observations, subtracting the population mean, squaring that, and then dividing by our population variance, and then adding all of those up. So this, remember, is just a standard normal, right? And then you're squaring the standard normal and summing them all of these up, so we know that w is chi-squared, and that's one of our prerequisites. Here is where the proof gets to be interesting. So this is the same thing as the sum from I is equal to 1 to n. The bottom stays the same. Actually, I'm going to bring this sigma squared out because I don't want to write sigma squared every single time. But this is the same thing as saying xi minus xn bar plus xn bar minus mu all squared. So basically, we're adding something and then subtracting something, so we're adding 0, so we're not changing this. But what this allows us to do, I is equal to 1n, is then we can kind of put brackets here and use the square formula or the binomial formula. So this is going to be equal to the my x plus 2 times another term, or we've got 1 to do is we're going to separate the sum out and we're going to divide by sigma squared for all.
He forgot the hat about xn, but it
of them, because this x squared, and then we're going to add 2.
Did he actually forget it? Did he actually forget it? Yeah, I think he forgot. Yeah, he forgot.
Then I can leave it out. I can do whatever I want. It's a constant. So I'm going to leave it out here, and you'll see why in a moment. And then this sum, the sigma formula, the sum, is basically going to go in, and xn bar minus mu doesn't depend on I, so that's a constant, right? So I'm going to bring it out, xn bar minus mu, and then I'm going to have the sum, because xi definitely does depend on I, from I to n of xi minus xn bar, right? So that's what that sum is. That's the second term. And then the final term is going to be plus the sum from I is equal to 1 to n xn bar minus mu all squared over sigma squared. Okay, now where do we go from here? Well, the first thing we want to notice is this little thing over here. So this portion, this sum over here, is one of our prerequisites that we spoke about earlier, and it's this thing over here. When I take the sum of my observation equal to 0, I minus n2, there's another thing that we need to notice, which is basically that in this term over here, right, the second term over here, I don't have any single I don't have any single variable or I don't have anything in the sum that depends on I. So basically this is just a constant being summed up n times, which means I'm just going to have n times that constant.
Yeah.
So I'm going to have I
Yes,
But this little thing over here, remember that sigma squared we're dividing by it, we can just bring it out. So this is going to be 1 over sigma squared. Okay, this thing over here is equivalent to this thing over here. So what we can then write is this is equal to minus over sigma squared. Okay, and remember that this is equal to W, which is what we had at the top. And remember what W was. Okay, so now what we're going to do is we're just going to define some new terms just so that we don't have to go about writing all of these horrible fractions. So n8 u whole term over here is just some normal distribution, some standard normal random variable squared. And the reason we know that that's a standard normal squared is because of this fact over here, basically. Okay, so now we have that, and remember we know that u squared is a chi-squared with 1 degree of freedom.
Mm-hmm.
Okay, so
let me pause 1 second. Okay, I'm back. Let's go.
We have that W is equal to H plus U squared. Now, remember that we know that, I don't know if I can, I've still got space. Okay, so we know that W is a chi-squared with n degrees of freedom, and we know that U squared is a chi-squared with 1 degree of freedom. So, if we take the moment generating function, right, of W of t, but using this formula, right, we know that it's going to be equal to this is basically going to be equal to E of ETW, which we can use the actual definition that we have for W that we've manipulated basically, to be e to the t of h plus u squared. And then when we bring that out, it's going to be e to the h plus tu squared, which is e of e to the th multiplied by e to the tu squared. And now this is important because we've got this function of u and we've got this function of h. Now remember that h is equal to n minus 1 s squared over sigma squared. So h is a function of our sample variance, and u squared is, well, our definition of u squared is nxn bar minus mu squared all over sigma squared. So u squared is a function of xn bar. So we have a function of our sample variance and a function of our xn bar, which is our sample mean. And based on...
Wow, I just built the most
this fact over here, that our xn bar and our sample variance are independent, it means that any function of those two things are independent. So that means that h and u squared are going to be independent, which means if I take any function of h and u squared, those are going to be independent. So I can separate this expectation out, right, multiplied by e of e to the tu squared. But this over here is just equal to the moment generating function of h of t multiplied by the moment generating function of u squared of t. Okay, so now we have this result. I'm just going to bring us back up here to the home stretch. So I'll just write out what we have. Okay, equal to moment generating function of u squared, bring us back of t.
Okay, why did he get
Any function of h and u squared, those are going to be independent. So I can separate this expectation out, right, multiplied by e of e, the are going to be independent. is the moment is the squared of the bar and which is our sample mean.
They are in the to depend because
and based on this fact over here, that our xn bar and our sample variance are independent, it means that any function of those two things are independent. So that means that h and u rate this. So w is the moment generating function of u squared of t multiplied by the moment generating function of h squared of t. And we also know that w is chi squared of n and u squared is chi squared of 1, which means that the moment generating function of w should be equal to 1 minus 2t to the power of minus n over 2, and the moment generating function of u squared should be equal to 1 minus 2t to the power of minus a half. So then using these two facts and this fact over here, we can write that the moment generating function of h of t is equal to the moment generating function of w divided by the moment generating function of u squared of t, which is 1 minus 2t to the power of minus n over 2 over 1 to the power over, right-hand side. That is equal to our right-hand side. If we look at what our right-hand side was, right? This should be n minus 1 over there, because remember v is chi squared with n minus 1.
yeah.
So that right-hand side is squared.
So he basically improved. Okay. Very interesting and very complex. I don't think I could have done it myself. Thank you very much for sharing. Let's continue.
Мінус 1 ступенем свободи. Так ось ми для побудови критеріїв цю оцінку перетворюємо, а саме домножаємо на n, ділимо на гіпотетичне значення дисперсії, так, щоб в разі правильної основної гіпотези отримати фіксований розподіл хі квадрат буде конзистентним. Тоді х для рівня.
Easy peasy lemon squeezy. You got the formula. You know that it's high squared. It's easy from this point to just obtain the critical value for the confidence level alpha. He squared n minus 1 minus alpha is our critical. Okay.
1 мінус альфа на 2 до нескінченності. Більш складний випадок, коли у нас є дві вибірки, x1 і так далі, xn кратна вибірка з нормального розподілу невідомим середнім μx і невідомою дисперсією сигма квадрат x, y1 і так далі, yn кратна вибірка з параметрами μy і сигма y квадрат, теж нормально розподілено. І оці дві вибірки, звичайно, припускаються незалежно. Основна гіпотеза, що відношення невідомих дисперсій сигма квадрат x до сигма квадрат y дорівнює певному фіксованому додатному значенню r. Звичайно, це r дорівнює одиниці, тобто частіше за все перевіряється гіпотеза про те, що дисперсії є однаковими. Ну і, як завжди, побудову критерію ми починаємо з вибору оцінки для...
Okay. So we are moving on. Yeah, sorry. I zoned out. So he's talking about the next case, which is just the relation of ratio of two variances. Basically everything the same. We don't know anything, as I understand. And our zero hypothesis is that these two variances have the ratio which equals to r. R is more than 0. And yeah, he says that usually r
Статистичні оцінки йде
r
відносно.
will equal to 1, which would be a hypothesis that the variances are equal.
Дисперсії, да? Їхнє відношення.
So he's creating again the yeah, now he's using n-1 for unbiased estimation of our variances. Thank you. Why couldn't you use that before? Anyways, so he's using that, and he's using this for the two distributions, estimating the variances in them. And then he's dividing one over another, and then he's saying that this has their ratio, yeah, has this distribution. What's it called? This is the Fisher. Is this Fisher distribution or not? Yeah, probably. Doesn't matter. Doesn't matter. Anyways,
Має розподіл Фішера з n
Fisher distribution, right? So yeah.
з 1 та n-1 ступенем свободи.
Yeah.
Це розподіл відношення хі квадрат розподілить незалежно.
Yeah, Fisher distribution is just the distribution which consists of two independent he-squared division of two independent he-squared distributed variables. So,
Прощує відношення на відому складномноження. І ось така статистика.
blah blah blah. This is the statistics for our criterion. We use here, instead of this, we use R because this is the statistics for zero hypothesis, H0, right? And here we know that this distribution equals to R. So we just put R in here and calculate our criterion. Pretty easy.
Критерію і виходить. Тоді, якщо ми відхилятимемо, да, значення, які менше квантиля відповідного розподілу рівня альфа на 2, або більше квантиля рівня, є консистентним при НТМ. Ну і варто зауважити, що якщо верхні критичні значення, звичайно, в таблицях ось для цього розподілу Фішера є, нижніх критичних значень зазвичай немає, але їх легко обчислити, скориставшись такою властивістю розподілу Фішера, що розподіл Фішера з n-1 та n-1 ступенем свободи – це одиниця поділити на розподіл Фішера з n-1 та n-1 ступенем свободи, тоді квантиля верхні та нижні співвідносяться саме таким чином. Це дозволяє знайти критичні значення.
He's talking about how to get these quantils for our level alpha divided over 2, and he's telling that one of the life hacks, one of the hacks that you might have is actually doing this, and then kind of if you have just one pre-calculated definition for the quantile, you could actually get the opposite one, the second one, as well. So this is pretty useful. Let me write this down. So ratio of variances. Mu y sigma y. I don't know why. Why when it's love to see you cry? Y equals R. Usually R will equal to 1. Again, obviously. So we use S squared is 1 over n minus 1 sum from I to 1 to all the way up to n xi minus sample mean to the power of 2, as we just saw in the previous video. So we are saying that this has the distribution of sigma squared over n minus 1 high squared n minus with n minus 1 degrees of freedom, again from the previous case. The same goes for our second sample y. This the exactly same thing. We only change indexes. M minus 1 high squared m minus 1. So now what we do, we say that the ratio s squared x to s squared y has the same distribution as sigma squared x sigma squared y times high squared minus 1. And this has the Fisher distribution. With n minus 1, m minus 1 degrees of whatever, freedom. And we say that the statistics, not statistics, but just statistic for the test. So he's saying statistic for the test is this motherfucker here, which is basically just as we mentioned, just sig sx squared divided by sy squared 1 over r, and that has the Fisher distribution minus 1 m minus 1. If h0 is correct, he defines a critical region D. Critical region is the region in which, if our statistic falls into that region, it is highly unlikely for our statistic to fall into that region if h0 is correct. So that's that. If our statistics falls here, we reject our zero hypothesis. So we say critical region D equals f is either less or equal that, or it's more or equal m minus 1 minus alpha divided by 2. Okay, great. Perfect.
Критичні значення з таблиць, які містять, як я сказав, лише верхні критичні значення. Ну, але насправді у нашій частині простіше скористатися вбудованими функціями в статистичних пакетах або інших іншому прикладному програмному забезпеченні.
1 hour almost 1 hour in. Okay, great.
There's so much information to look.
Fuck you. The next. Sorry. The next step is multinomial distribution. Whatever. Let's go.
Вітаю! У наступних декількох відео ми поговоримо про майбутнє.
Oh, it's not just one. It's actually... I guess all these videos are going to be on this one topic. Let's see.
Найпопулярніші статистичні критерії це так звані критерії фі квадрат. І у цьому відео почнемо з того, що розглянемо статистичні властивості так званого мультиноміального розподілу. Що таке мультиноміальний розподіл? Це не що інше, як просто дискретний розподіл з будь-якою скінченною кількістю значень, таке узагальнене біноміального розподілу та замість двох значень будь-які К значень. Тут за номер.
He's saying what is multinomial distribution is basically distribution with some discrete values. That's it. You may have k discrete values and you have some probability of obtaining one of the value.
Ромбленими цифрами від 1 до К. Ну і в застосуваннях такі розподіли пов'язані з тим, що називають категоріальними змінами або номінальними ознаками. Англійською categorial або nominal variable. Ну, це будь-які ознаки, що набувають скінчену кількість значень, типу як стать, чоловік, жінка, або бінарні ознаки, є певна властивість, немає певної властивості, або рівень освіти, неповна середня, повна середня, неповна вища і так далі. Ну, якщо ми говоримо про статистичні властивості, маємо ми розглянути кратну вибірку з такого дискретного розподілу, отже, нехай є x1, x2 і так далі, xn, незалежні однаково розподілені величини, набувають значення цих, що я занумерував натуральними числами від 1 до К, з ймовірностями йоти значень, набиваються з ймовірністю θ йот. Ну і якщо ми розглядаємо статистику, ми вважаємо усі ймовірності невідомими, отже, у нас К невідомих параметрів розподілу, θ1 і так далі, θk, іншими словами, такий векторний параметр. Ну, насправді можна так умовно казати, що розмірність цього вектора справжня така ефективна К-1, тому що сума цих всіх координат дорівнює одиниці, це ймовірнісний розподіл. Отже, К та координата виражається через решту, це я маю на увазі, коли кажу, що ефективна розмірність К-1. Ну і щоб оцінити статистично невідомі ймовірності всіх значень, можна скористатися методом максимальної вірогідності. Вірогідність – це доводок ймовірностей окремих спостережень. І легко побачити, що це можна переписати так. Доводок θ йот в степені ню йот. Та ню йот – це частота результату йот, кількість тих значень вибірки, які рівні йот.
Okay, he's saying that this is the frequencies of our results, so number of such xi's for which xi equals to j. So basically, yeah, this is just frequency of obtaining our result in our data set of x's. We get probability likelihood of getting this result is it's just you multiply, you've got k different values, not variables, values. You got k values. For each value you get some probability, so you just multiply all of it, each probability to the power of basically number of times you obtained this value for this probability, and then you multiply this for each individual probability. Basically, yeah, you just it's like with coins, right? The more time you flip coin, and the more you got results from flipping the coin. The more times you multiply each of the results, more times you multiply, you multiply this probabilities, and thus the less likelihood, your likelihood goes down, which is kind of logical. The more times you flip the coin. Do you still work? Yeah. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I hope this works. So the more times you flip the coin, the more I'm tired. Anyways, I know what I want to say. Let's continue. So this is the likelihood. You just multiply all of your probabilities that you got in your sample. So here, respectively, the estimation for each of the probability is just number of times you saw the variable. The value, not the variable. Number of times you saw the value of this probability divided by number of data points you got in your dataset.
Легко знайти точку максимуму, скориставшись методами математичного аналізу. Ну і розв'язок, як не важко переконатися, це добре відомі нам емпіричні відносні частоти. От йод з кришкою, йод поділити на n. І вони мають всі властивості, які ми вже знаємо, емпіричних відносних частот. Це незміщені оцінки справжніх ймовірностей, строго консистентні.
This estimate is unbiased and a strictly consistent estimate of the true parameter theta.
Ні, асимптотично нормальні. А ось що стосується асимптотичної нормальності, насправді нам потрібна більш сильна властивість, а саме така як сумісна поведінка асимптотична частот. Що я маю?
Okay, let me write this down. So we got from discrete distribution, probability of x1 equals j is theta j. J goes from 1 to k. Great. Now we say that theta, which is vector of all of these probabilities, k probabilities, is unknown variable. That's why I make this distinction between variable and value, because theta is variable, and with each of the theta k, theta I, theta 1, theta 2, with each of these thetas there is one value that corresponds to them, some discrete value, and we got frequencies of our variables. Nu j is number of such as that x I equals j. Great. J equals 1. Okay. Okay. Likelihood. Is just the multiplication of all of our observed probabilities. J equals 1. Okay. Great. Оцінки estimates. So I guess he is just jumping ahead and saying that from this likelihood you can get, using method of maximum likelihood, you can get estimates for thetas, and you say Yeah, we should do this probably by hand. We should derive this with our own hand, but come on. Let's just skip it for now. If I ever need it, I will derive it, but I don't think I will ever need it. Of maximum likelihood, empirical frequencies. This is called empirical frequency, basically. When you divide, for example, sample mean is the estimate for the mean, right, of the distribution, and yeah, I think it's also empirical. Anyways, let's continue. Equals nu j divided by n, j equals 1 to k. Alright, Nesmission, unbiased, strictly consistent. Great. Next, asymptotical. Now he's proven the asymptotical properties of these frequencies, specifically asymptotical normality.
А саме така як сумісна поведінка асимптотична частот. Що я маю на увазі? Я маю на увазі, якщо ми розглянемо такий кавомірний вектор, де йота координата дорівнює ню йот мінус n бета йот поділити на корінь з n бета йот, да? Ось такий вектор збігається за розподілом до нормально розподіленого вектора, середнім 0 і матрицею коваріації, де це елемент з порядком йот дорівнює дельта йот, це дельта Кронекера, да? Одиничка для
To prove its asymptotical normality, you have to look into all of these frequencies, not just one by one, and that means that we are looking at this vector. He constructs this vector of values, right? And he's saying that this vector tends to converges to has weakly it converges by distribution to normally distributed vector with mean 0 and covariance matrix C, which is this.
Навпаки, так? І на скорінь степі йот тета. Отже, у нас по діагоналі порядком, це елемент з порядком йот дорівнює дельта йот, це дельта Кронекера, так? Одиничка для йот дорівнює і 0 навпаки, так?
So this is basically either 0, 1, depends on the yot, on the j here.
І на скорінь степі йот тета.
He is calling it delta Kroneker's delta. Let's Google it. I'm really bad at Kroneker. Google knows everything. Here. So basically all the elements on the diagonal are ones, others are zeros. Great. Let's move on.
Отже, у нас
So basically here we either subtract 1 minus, so anything which is on diagonal of our matrix is going to be 1 minus this, and anything which is not on diagonal is going to be just 0 minus this, so just minus this multiplication.
По діагоналі стоять 1 мінус тета йот просто, да? Поза діагоналі мінус корінь із тета йот в цій матриці коваріації. Ну і нам навіть важлива не настільки ця асимптотична нормальність, да, сумісна, скільки наслідок з неї, те, що сума квадратів координат цього вектора збігається при n прямої до нескінченності до випадкової величини.
Beautiful. This is just beautiful. So you may be wondering, why the fuck do we need this asymptotic normality, right? Why do we need this complex vector which converges to some normally distributed vector with some weird covariance matrix? Because this is just beautiful. Because the sum of these points, yeah, is going to converge to high squared distribution.
Що має хі квадрат розподіл сумісна, оскільки наслідок з неї те, що сума квадратів координат цього вектора збігається при n прямої до нескінченності до випадкової величини, що має
That's just beautiful.
хі квадрат розподіл з k мінус 1 ступенем свободи. Ось k мінус 1 якраз за рахунок того, що у нас ефективна розмірність вектора імовірності є k мінус 1. Ну і якраз оця збіжність розподілу нам стане в нагоді, щоб побудувати відповідні статистичні.
This is just beautiful because I've been using in my work this high squared distribution and tests based on this high squared distribution for categorical variables a lot of times, and I never really understood why. I just read it in a cookbook and it worked. And only now I'm coming to realize why the fuck it worked. It's beautiful. Okay, alright. Let me see. Okay, I still have time to study here. Let me just write this down. So again, asymptotical normality. Our vector nu j minus n times probability of j divided by n times probability of j for j from 1 to k converges by distribution to this normally distributed vector n tends to infinity, where C equals this matrix I L J L minus 1 J and other probability, two probabilities, and it goes from JL1 to K. Great. And from this we can conclude equals 1 nu j minus n theta j squared n j tends to high squared distribution. Beautiful.
Критерії.
Very beautiful. Elegant. Elegancko, as they say in Poland.
Про критерії.
Okay, so now four videos. I'm kind of tired. Should I continue? 1 hour? Yeah, I should continue.
Квадрат для мультиноміального розподілу. Ну і давайте згадаємо, про що ми говорили в минулому відео. Нехай у нас є кратна вибірка з дискретного розподілу, да, з невідомими імовірностями окремих значень, отже, x1 і так далі, x1 гіпотеза. Ну і
Okay, he's formulating main hypothesis. This is high square test. High square test. Criterion or test high square. So this is pretty important to understand. I once failed an interview to a big and cool company, I would say. Many people want to work there, and I failed the interview because of this fucking high square test. I didn't remember all of the prerequisites for this. So, high squared criterion. We got our data, we've got our probabilities, we've got our values. The main hypothesis is that theta equals to some vector of fixed probabilities. Fuck. How it's called? Discrete sample. Okay, we got our probability of we got our null hypothesis. Is equals to some vector p1 pk. Goodness of fit test. Goodness of fit test. All right.
це
And I think on that interview I just fucking didn't say exactly that high squared is used for categorical variables, categorical data for this, not for any kind of data. I think that was my mistake. I could see it in the interviewer's eyes that he was disappointed in me. I was disappointed in me myself, so can't blame him.
відноситься до так званих критеріїв згоди, англійська Goodness of Fit Test, які якраз вивчають узгодженість з певним розподілом. Зараз узгодженість з дискретним розподілом, що набуває значення 1 і так далі К, з ймовірностями P1 і так далі ПК. Статистика критерію – це якраз...
Yeah, he's high squared. Yeah, correct. So is the equals so this is just our statistic for our test, obviously from the previous slides. This is what I was talking about. Beautiful. And it tends, it goes and converges to x high squared k minus 1 and goes to So,
Нормально. Чистою статистикою, хі квадрат розподіл.
so we can get the critical value is the quantile of level 1 minus alpha for the high square disk distribution with asymptotic level alpha consistent. Great.
Пускай мінус 1 відхрещений рік це нескінченність. Це, щоб запам'ятати. Це зараз є таке мнемонічне правило. Сума О мінус F в квадраті поділити на E, де О це від англійської абсурд, те, що спостерігається. Частота.
Okay, this is his just he is explaining this rule of thumb, rule by which you might easily remember this high square test, basically which goes like sum of observed values minus expected values to the power 2 divided by expected values.
Значення йод. Да, це що очікується за правильною основною гіпотезою. Expected. Да, за правильною основною гіпотезою.
High squared is O minus E divided by E. I remember studying this some long time ago. It's not hard, it's just that I didn't really care for this for a long time and I forgot totally forgot everything that I've learned.
Кількість значень рівних йод має біноміальний розподіл з параметром P йод. Тоді математичне сподівання це добуток параметрів P йод. Ось приклад. Да? Перевіряємо гіпотезу про те, що
Okay, that's a lie. I'm really shit. That data scientist. I was shit.
крайній кубок симетричний. Рівень значущості 5%. Нульова гіпотеза якраз нейтральна, да, як ми говоримо.
This is an example of Tosin. What's called in English? Fuck. I don't know. What do you toss, English people? Not the coins, but the cubes which have 6 sides and 6 numbers and with numbers on each side. Roll dice. Dices.
Про симетрію. Ось ми підкинули цей кубик 20 разів і такі результати. Да?
So he is covering this example. He's saying he's considering 5% of accuracy of significance level. He's saying the basic hypothesis is that our cube is symmetrical. So he did 20 tosses and he got these results. This means 0, no result. And you can see other results for each of the numbers.
Це виконано двічі. Жодного наперед.
You calculate the criterion for the high squared.
Порахувати, так? Рахунок набуває.
0.4 is more than our level of 5%. This means that we do not reject our hypothesis, because remember, the critical region starts below 5%, right? So everything that falls, which has this p-value of more than 5% in our case, basically does not fall into the critical region. In this case, it didn't fall.
Таке значення.
I think if we if we set 10% significance level, I think we could have already said that we could have rejected zero hypothesis.
Або більше. Да? Наш так суперечить гіпотезу оці. Також можна цей критерій застосовувати як критерій.
Now this is the question that I maybe didn't get wrong on that interview I mentioned earlier. He's saying that you could also use this high squared test for continuous distribution. How? Probably by cutting it into regions and then basically basically converting your variable from continuous to categorical.
Згоди для... Так, і щоб застосувати розбити чи це від номер інтервалу. Да? Ну і насправді розбити на К частини можна по-різному. Да? Ось.
He's saying that it's best if our if these probabilities, this is a PDF probability distribution function. Zero hypothesis is that our PDF, unknown PDF, equals to some known, some PDF that we created. So we split our data into these chunks, and then he's saying that into these chunks, and then he's saying that probabilities of these chunks should, not must, not have to, but should, not need to, but should be roughly the same. We calculate frequencies for our again observed values.
Отримати найточніший критерій, краще розбити, коли багато неперервних розподілів буде те саме і так далі. Да, ну і насправді побудований критерій не буде консистентним, тому що є дуже багато розподілів, для яких ми ось таким розбиттям отримуватимемо один і той самий дискретний розподіл. Да? Багато неперервних розподілів будуть давати один і той самий дискретний розподіл. Ну, навіть є вже безліч розподілів, які ймовірність потрапляння в цей інтервал, для яких така сама, і для яких в такий інтервал ймовірність така сама і так далі. Да, ну і щоб зробити його консистентним, треба взяти кількість оцих інтервалів, да, залежно від n, щоб вона зростала з n. Ну, за певних там складних припущень на розподіл цей критерій буде консистентним, коли k пропорційно логарифму n. Ну, в принципі, з практичного погляду, ну що означає ця пропорційність, да? Практично, значить, десь де n починаючи з 20, та беруть k там десь 7, для n порядку там 50k дорівнює там від 15 до 20. Для...
So he's saying to make this test consistent, to make this test consistent, you want to set such a k which roughly equals to the natural logarithm of n, of your size of your sample. Why? Because so he's saying that many distributions have, if you divide those distributions, continuous distributions, into the same chunks, they would have same into chunks. They would have same probabilities in those chunks, especially if you choose big enough k. So that means that you want to your k to be dependent on the size of your sample.
Там порядку 100 k десь 20 і так далі. Ну, взагалі є таблиці рекомендованих значень k для різних.
He's saying that there should be tables of recommended values for k depending on n. I guess it should be already coded in the Python and R libraries.
Для різних розмірів вибірки.
Okay, great. Fucking awesome. Okay, I think we can end at this point. I'm pretty tired. We've covered 3 videos today and we got only 3 videos to go. Yoo-hoo! We are almost there. and all three of them are about the same chi-squared test. So they should be quick and interesting and quick, which is good. So see you next time, probably tomorrow or Thursday, we'll see. And yeah, if you got, I don't know how many people will watch this. I'm doing this for myself, but if you find anything that this helps you, or do you wish me to dive deeper into one of the topics, yeah, just let me know. I will read the comments. Anyways, see you.